Hi, my name is Brian Valladares, and this summer I worked in the Cummings group under Dr. Keita Tanaka. My project is the synthesis and characterization of N-Heterocyclic Iminophosphazenes, NHIPz, a novel subclass of superbases. Some background on superbases in synthetic chemistry. Superbases are defined by their basicity relative to proton sponges and their pK being greater than about 18 in acetonitrile. The major limitations of superbases are the complex synthetic pathways that are needed to be taken to furnish these molecules. However, their utility lies in their ability to access high pK pronucleophiles. And this work in particular looks to underscore the synthesis of these N-Heterocyclic as a novel subclass of superbases with applications in catalysis and reaction development. Figure 1 highlights the previously reported superbases alongside the estimated pK of our molecule N-Heterocyclic of about 21. Now, the novelty behind N-Heterocyclic lies in their cyclic rigid structural framework, and this is a feature that isn't often seen in many commercial superbases, but also allows for a high level modularity. The molecule itself is furnished by a 1,3 cycle addition, which is allows for the azophosphine and the alkene to interact in a cyclic nature to form the N-Heterocyclic itself. This high selectivity allows for an extensive amount of optimization by being able to modify the aromatic group, the alkene, and the potential synthons connected to the phosphorus atom. Now, in figure 3, we have an example of a base catalyzed asymmetric reaction using these different superbases of DBU and MTBD. Both of which have a pK of about 24, but the overall yield of these reactions are very different. This is attributed to the sterical clouding of MTBD and shown in the transition state, indicating inhibitory base binding, which essentially highlights the dissociation of the base that uses the sterical clouding of this superbase from the complex to complete the catalytic cycle. And this circles back to our discussion of N-Heterocyclic because the high level modularity allows for a high level of optimization for specific reactions depending on the sterical needs of the molecule and its interactions with other components of the reaction, thus allowing for a high level of flexibility within the molecule itself. Moving towards the synthesis of the N-Heterocyclic itself, we started off with 5-hydrazine. And this underwent a cytoprotection to give us product 4, which was oxidized to give us product 3, and this was treated with a phosphochloride substitution, so to remove the cytoprotection, and this gave us product 2, an azophosphine, and this azophosphine was treated with DMAD, the alkene, to give us our final N-Heterocyclic. And next to that, there is a computational model, which was inspired and necessary from some of the limitations the group faced as indicated in figure 5. Here in figure 5, we have the toluene substituted aromatic group compared to the xyl substituted aromatic group that was actually used. Originally, we had been using this toluene based cytoprotected group, and this was treated with the same phosphochloride compound. However, 2B was our target molecule. However, when this azophosphine formed, it underwent a 1,3 cycle addition with 3B, the starting reagent, and created a lot of different side reactions and messy spectra, indicating a plethora of different side products that were undesired. We went back to the drawing board and realized that by creating some sterical clouding around the nitrogen groups of the cytoprotected atom, of the cytoprotected molecule, we were able to reduce the side reactions and prevent the 1,3 cycle addition from prematurely occurring by the azophosphines formation. And here, in terms of characterization, we did extensive proton NMR indicating clean formation of the N-Heterocyclic and its starting materials. And we looked at the carbon NMR, looking at figure 7, and in particular, we're interested in the phosphorus carbon bonds, and the coupling constants between them, as they had been scarcely reported throughout literature. And our primary form of characterization was these phosphorus NMRs of figure 8, indicating nice formation of the N-Heterocyclic overall, and was a useful way of keep track of all the different types of products that were formed. And in terms of future work, we were looking to see and apply the NHIPz to known superbase catalyzed reactions and compare the reactivities and selectivities. But before doing so, we would also want to accomplish some PK analysis through NMR titration alongside X-ray crystallographies, as this was something the group envisioned, but due to time constraints, we're unable to get done this summer. And in terms of this characterization, I think it would allow for a deeper understanding of the compound's pK modifications, depending on the different, I guess, modifications done to the molecule and different adducts that can be synthesized. And with that, I'd like to thank Professor Cummings, the Cummings Group, Dr. Tanaka, the MIT Chemistry Department, and the MSRP program for allowing me this chance this summer to work on such great research. And thank you again for taking the time of looking over my research.